surfaces and fourth dimension.
Perfect. Thank you very much for inviting me. Thank you all for coming. Thanks particularly to the Fernholz Foundation for supporting the visit and to Princeton, of course, for hosting me. This and the next few lectures are almost all about work of other people, but then later in the series and briefly today, I'll talk about some joint work with Lipshitz Sharkar. What other announcements in this slide? Well, this part I'll explain later in the talk. This is a QR code to this URL. It'll get you to the web page for the talks. You can also find it with Google. That has a description of what's coming, but also a supplement to these slides. So lots of things are going to be a little bit hand-wavy on the slides because I want to say lots of things and not spend a lot of time on making them precise. But then a lot of them I made precise on the supplement. It also has some exercises. So if you want some problems to do that are actually solvable related to it. So I'm treating this a little bit like an actual course, and each lecture will have some accompanying homework. But you don't turn it in. If you do turn it in, I don't grade it. OK, so I wanted to dedicate the lectures to Bill Browder, who passed away last winter. I was an undergraduate here 25 years ago, give or take, and had the great privilege of studying algebraic topology in a reading course with Bill at that time. So I didn't know him as a friend or as a person, but I knew him as a student, and it was really a wonderful experience learning from him mathematics and also some meta-mathematics about thinking about mathematics. So, you know, among many great experiences here, that was high on the list. Maybe I will share one piece of sort of useful piece of advice about doing mathematics or thinking about mathematics that I learned from him before going back to the talk, which was he explained to me, if you think you have most of one proof of something, you're trying to prove something and you have most of the proof, that's good. If you think you have most of 3 proofs of the thing, that's a bad sign, because that tells you that on some level you don't really believe any of it. So 1 proof is good, 3 proofs is not so good. OK, so on to the overview. One problem with slides, let me say that first. One problem with slides is the thing you were just looking at disappears when you go to the next slide. So I've put the key points from the previous slide, or in this case 2 slides back. It's always in the top left. So this green box in the top left tells you it's just the main points of the previous slide. So hopefully the thing that you wanted didn't disappear. This is a bit of an overview of the course. So today I'm going to talk about knots and surfaces and some things we know about them, and then conclude with some open questions, a little bit of techniques and some open questions. This is going to be very general, so aimed at well, you're always sort of I'm always talking to myself, so I'm thinking about this is sort of aimed at what might I like to have heard, you know, as a first or second year undergraduate, and maybe as a third or fourth year undergraduate. So this should be accessible to everybody, and the experts are going to be fairly bored, so I'm not offended if they walk out or just look really bored. Then the next 3 lectures are an introduction to some of these techniques of Khovanov homology. And the same sort of at upper year math majors, beginning graduate students, and the last 3 are aimed at, you know, sort of older graduate students or faculty in topology if they're interested. I'll say a little bit more about prerequisites at the end of the talk. Of course, you may have noticed it's not as clear in this, but the text gets lighter as you go down, and that's because the certainty that this is what happens gets less and less. So this is the current plan, but I don't think I've even bothered to write abstracts for the last few talks yet. We'll see who's actually coming, and I'll try to do something that corresponds to the audience and how far behind we get. OK, so that was a general overview. What are we doing today? So here's the sort of statement I want to be able to state precisely and say a few words about the proof. So it's a theorem from 2021 due to Kyle Hayden and Isaac Sundberg. Kyle was, I think, a postdoc at the time, and Isaac was a graduate student. So this is a theorem of, at that time, young people. Now they're, of course, a little older. Kyle's now at Rutgers, Newark, so he's still in the neighborhood. So this is an exotic pair of disks. Well, it doesn't look like a pair of disks at all. So I want to say in what sense is this a pair of disks? How does this represent a pair of disks? And what does the word exotic mean? So the beginning part of the talk is sort of what does it mean to have an exotic pair of disks? So I'm going to talk about just some general background about services. For experts, I'm going to sort of lead up to classification of services. So famous old theorem that everybody above a certain mathematical age knows. And then I'll conclude with a little bit of an announcement of some of the stuff that's weird in dimension 4. Then I want to spend the second half of the talk talking about how do you visualize services in 4 space. How can you represent them in a way that you can get your hands on? And at the end, I'm going to talk very briefly, just one slide, about the general strategy for proving these things, and then a few slides of open problems. There are lots of beautiful related open problems, and so I thought I would highlight a few of them. This is the graph of the difficulty of the slides. I rated each one 0 to 3. 0 means there's no mathematical content. We're at a 0 because there's no content here, except, I guess, a picture. And then some 1s, 2s. So as you see, it goes up and down. The trend is a little bit upwards. But if you're feeling bored, there's a chance something more interesting is coming in the next slide or two. And if you're feeling lost, there's a chance that it will, the next slide or two will be a little bit easier. Of course, if you're feeling lost, you should feel free to ask a question also. OK, on we go. OK, so curves and services, 3 slides about curves, 2 slides about what it means for service equivalent, and then some classification of surfaces, and then we'll talk about what's weird in dimension 4. The difficulty is here. These are the tiger ratings. This is a 1 tiger slide. So a curve is a subset of Rn which locally looks like an open or closed interval. Here I've drawn 4 of them. Locally means that near each point on the curve, you can parameterize it in a nice way by a little interval in the real line. So there's a continuous bijective map from a little interval in the real line to a little neighborhood of your point for every point in the curve. Curves can have boundaries, so that interval could be just half of an interval if it had boundary. Like, let's see. I'll say that in a sec. Sorry. All my curves are going to be closed bounded subsets of Rn, just to avoid having to make lots of special cases later. Curves can be closed or not closed, however, and have boundary or not boundary. They can be closed or have boundary. Try again. They can be smooth or not smooth. So wait, I just said they're all closed subsets. Closed means 2 different things. This is a closed curve in the sense that if you trace around, you get back to where you started. It closes up on itself. This is a closed subset of the plane, but it's not a closed curve. Okay, so these 2 are smooth. This one closed with boundary. This is not smooth. That's also not smooth. More on this slide? No. Okay. Here are 2 more curves. These are drawn in 3 space. So these are 2 curves in 3 space. They should be, of course, very, very thin, but I gave them some thickness so you can see them. Intrinsically, all curves are the same. All continuous curves are continuously the same, closed ones. And all smooth curves are smoothly the same. So this is 2 statements. So that is, you can find a continuous bijection between any simple closed curve, any closed curve, and the standard closed curve. So there's a bijection. As you walk along the bottom, it turns pink. The one at the top turns pink. So the points are getting paired up under this map. And I think I set this to just keep going. And so we can sort of just watch the pink go round and round in a sort of meditative way. I think it's a 1-hour talk. OK, I stopped it. Extrinsically, if you're not constrained to lie on the curve, you see all of space. There are lots of different closed curves in R3. The one at the top is clearly different the way it sits in R3 from the one at the bottom. So intrinsically, there's only one. Extrinsically, there are lots. And this difference is being knotted. Sorry, I'll go to this in a sec. So the difference between being intrinsically the same and extrinsically different, that's what knotting is. Curves can also be locally weird in how they sit in R3. This is a simple closed curve. It winds around many times, but smaller and smaller and smaller and smaller and smaller. It's not locally flat. defined locally flat in the supplement, so you can look there. But I'm only going to consider locally flat curves. So they're things that can be approximated nicely by nice smooth subsets of Rn, or by piecewise linear subsets. Again, if you want a precise definition, it's in the supplement. Everybody good? Great. More from curves. Again, we're trying to get to surfaces, but it's easier to understand curves first. It's a two-tiger slide. OK, so closed curves in R3 can be knotted. I'm not going to define knotted. I'm going to define what it means to not be knotted, to be unknotted. Okay? So an isotopy of your curve means you take your curve and you drop it in some fluid. And now your fluid moves around, so all the points in space move around with the fluid, and it pulls the curve with it as it moves around. Isotopy means you drop it in the fluid, starts out wherever it is, and then it moves around with the fluid. So that's a family of maps from R3 to R3. That's the fluid flowing for time t, starting with the identity. Every point starts where it starts. And then moving around, you ask, where's the curve at time 1? That's an isotopic curve to your original one. So there's an example of the curve is flowing around, and it started out with the left picture, and it's ending up, well, eventually with the right picture. Okay, so these two curves are isotopic. Peter's afraid of me. Yeah. He's afraid I'm going to tell stories about him, for instance. This notion of being isotopic is an equivalence relation. It's an exercise. These isotopies, so curves could be smooth or not. Isotopies could be smooth or not, depending on whether you require the function f to be smooth or not. Well, f and its inverse really to be smooth. And I promise I'm defining unknotted. A curve is unknotted if it's isotopic to the circle in the top left. Okay? And if it's not unknotted, it is knotted. That's just the easier way to define things. OK. Surfaces. Almost everything we said applies for surfaces. So a surface is a subset of Rn that locally looks like either a disk that's there or a half disk, like at the boundary. So at the boundary points looks like half disk, and the inside it looks like a disk. Again, I only consider surfaces that are closed and bounded subsets of Rn, but a surface can be closed or not. Closed means it has no boundary. It's closed in the sense that it doesn't have any boundary. So here is a smooth curve surface with boundary. Here's a smooth surface without boundary. It's a non-smooth surface without boundary. Here's a not smooth, in fact, not even locally flat. You can't, this light is a little bit too much, but sort of gripping, it's like pinching at itself more and more finely. So this is called Alexander's horn sphere. I think Alexander was maybe here. Does anybody know? Yes. So there's a nice local horn sphere. And again, I'm not going to consider these. All of my surfaces are going to be locally flat. OK. So again, there are various notions of equivalence for surfaces. Two surfaces are equivalent intrinsically if you can find a bijection between them. And again, you could talk about a continuous one or a smooth bijection between them. Extrinsically, you again want to think about putting your surface in a fluid and letting its points, watching the points on the surface be dragged around from the fluid. So the surface is made of something very, very flexible. So here's approximately the same thing again, but here's a torus surface sitting inside a fluid. I decorated the points in the fluid with gold foil so you can see where they are, and it gets dragged around. So this is an isotopy of the torus. These surfaces are all isotopic. I'm also going to talk about isotopy of surfaces with boundary, and then you usually don't want the boundary to move. So I've got a surface in half space. It's the half space behind the screen, and its boundary is right at the front of the screen. And I'm going to think about isotopies where the surface moves on the inside, but the boundary isn't allowed to move. So this is an isotopy rel boundary. OK. And again, knottedness means being intrinsically the same, but extrinsically different. So this is intrinsically the same as the old torus, but extrinsically different. OK, I'm going to say that more slowly on the next slide. So let me say that again. So here are two surfaces. These are intrinsically the same. So if you were an ant, and you want to describe where on the surface you are. In both cases, you can describe it by giving your longitude and latitude. So your longitude is, say, how far around in the gold direction you are, and the latitude is how far in the purple direction you are. And I mean, if you're an ant, if you've seen ants, they only sort of know locally what the surface looks like that they're on. And the ant can't really tell if it's on this surface or that surface. In both cases, it's got its position nicely described by two angular coordinates. A sphere is different. So on a sphere, you can still describe where you are by a longitude and a latitude. But something goes horribly wrong with the longitudes at the two poles. You can even see that. Like, this is colored by the longitude-latitude pair in terms of the hue and the saturation, how dark it is and what color it is. But at the north and south poles, something goes wrong. So the sphere is not the same as a torus, because a torus you can describe, this torus, that torus by a pair of angles, whereas here you've got some mess. The fact that they're different is why polar coordinates are such a pain. Okay, so I'm moving towards this theorem, famous theorem classification of surfaces. I need a couple more properties of surfaces to state it. It's giving the intrinsic classification of surfaces. We want to completely understand surfaces intrinsically. So the last thing I want is orientable. So surfaces are orientable if you've got a consistent notion of clockwise. So here's my ant standing on this cylinder. And it's counterclockwise, because I'm not unreasonable. So it has a consistent notion of counterclockwise. As it moves around, the notion of counterclockwise doesn't jump anywhere. But if the ant was instead standing on this Mobius band, as it moves around, the notion of counterclockwise does jump. Where does it jump? I put it there. I mean, I just chose to put it there. But you notice it flips from whether clockwise to counterclockwise. And that has to happen somewhere. OK, we've mostly seen that before. If you look at my Mobius band, you sort of think I did a crummy job drawing it. Let's acknowledge that. It's sort of crummy over there. And if you can, I'm not sure if you can see from back there, but there's a big color jump along that line, and it looks bad. Why does the Mobius band look bad? This is drawn using some 3D software called Blender. This was divided into, let's say, triangles. And in order to draw it looking smooth, it has an algorithm that uses the normal vector in order to smooth it out. So it looks at normal vectors of adjacent triangles to smooth out the shape that it's drawing. But the normal vector has to behave badly somewhere here, because this is non-orientable. So Blender struggles with non-orientable surfaces. So this is actually applied mathematics. I mean, in the sense that the techniques that are used for computer graphics, some of them work very badly for non-orientable things. There is such a guy. Hold that thought. So again, this is intrinsic. The ant on the surface can see it. One reason I like the counterclockwise thing is that's clearly intrinsic to the surface, whereas the normal vector isn't. There's a famous Escher picture called Mobius strip 2 that illustrates this beautifully. I'm being recorded and put on YouTube, and that picture is, I believe, still under copyright, so I didn't include it on the slides. But you should all go Google it, which will find you a copy of the picture. Except most of you have seen it before. Would you like to predict the next slide? So that was one property, orientable. The sphere and the torus were both orientable. How do you tell them apart? Well, you're going to go back to the ants. So for that, you need some geometer ants. So here are my geometer ants. These are produced by generative AI as opposed to the rest of the stuff. This is some version of Stable Diffusion, Flux.1. If you look at them for too long, you're going to feel sort of bad for these poor ants. Like that guy's got an odd collection of legs. But yeah, he's got a long neck. And also a little bit of B maybe in the backside of both of them. I can look up what the prompt was. It was an OK-looking prompt. So you take your ant who's living on the surface with his compass. That's what that vertical thing is. That was a generative AI's version of a compass. I kept getting pictures with like north, south, east, west, because it didn't understand what kind of compass a geometer uses. OK, you take your ants, and they subdivide your surface into triangles. So they divide your surface into triangles. So here's divide this into triangles. And you count the number of vertices, edges, and faces. And you count for this one, you see 5 faces in the front, and 1 vertex in the front, and some more faces around there. And it's a little bit hard to count, but you could do it if you wanted to. And you'd see that there are 12 vertices, 30 edges, and 20 faces. Well, some of you recognize the shape anyway, so you knew that already. You might worry that I can't count, which would be correct. 30 is really sort of pushing it, but fortunately the software counts for me, so it agrees. Okay, so you count that, and you take some other subdivision of your sphere into triangles. So here's another one. This had 162 vertices, 480 edges, and 320 faces. Again, it's nice the software counts that for you. OK, and there's a theorem of Euler from the 1700s. I should have made that more precise, but I didn't. For a sphere, you always, if you take the alternating sum, v minus e plus f, you get 2, indeed. 12 minus 18, 2. OK, and v minus e plus f, well, this plus that is what? 482, and I subtract 480, I get 2. OK, worked. That's encouraging. This number, v minus e plus f, is called the Euler characteristic in Euler's honor. Here's another shape. This is, you can't see it so well with the light on, but this is called Suzanne. It's a monkey. It's used for sort of doing tests of things in Blender. And if you calculate here, you get v minus e plus f. So there are 507 vertices, 1,005 edges, and 500 faces. That arithmetic is easy. You get 2 again. There's something to notice here, which is this is a square. Like those are squares, and you can't see, but somewhere in the ear there's some like heptagon or something. They're not all triangles, and it doesn't matter. They don't have to be triangles. Any polygons will do. On the other hand, if you had a torus and you subdivide it into triangles, you don't get 2 anymore. You get 0. Okay, so the Euler characteristic tells you that this and that, well, at least you get different numbers for the torus and that. And if you had a genus 2 surface, that's like 2 tori stuck together, you'd get minus 2, and a genus 3 surface, you get minus 4, and so on. One last thing I want to say here, maybe a better way to think of this than v minus e plus f is you've divided your surface into valleys, esplanades, that means like walkways, and fells, that's like hills. So valleys, walkways, and hills, and you count the valleys minus the walkways plus hills. So here the green are the valleys, and I've got these orange walkways, and these blue things are added last, the hills, and it gives you the same count. So I'm dividing it into handles there instead of into this triangulation. OK, it's going to show up again in about a slide. 2 slides. Everybody good? Questions? OK. Classification of surfaces. So this famous old theorem, classification of surfaces, said intrinsically, every surface with boundary is in one of these 3 families. So each family depends on 2 parameters, k and g. And this is what you see is what you got. So it's this one is a disk here where I've glued on some strips, as shown, and 2 of them are twisted. There, 1 is twisted, there, none are twisted. If you have a closed surface, that's like the case k equals 0, so it doesn't really make sense. That would be minus 1 of these things. But you take the k equals 1 case, and then you fill in the whole boundary with a single disk. Okay, so these 3 families is all surfaces. The first class are orientable. The next 2 are non-orientable, because you can see the sort of Mobius band is going to screw up the orientation, the clockwise there. This is an extremely powerful theorem. For instance, this surface is not on our list. It's equivalent to this one, it turns out. That is intrinsically equivalent to that one. It's sort of amazing that you would think that I'm just missing some things. I got lazy, but I'm not. This one is not on our list either. This is a picture used with permission from a paper by Hayden, Kim, Miller, Park, and Sundberg. This complicated-looking gizmo in 3 space, it's that surface on the list. So any surface you find anywhere is one of the ones on this list intrinsically. So it's really a very good theorem. Okay, how do you tell which one on the list you are? Well, you can build any surface starting with a bunch of cups, attaching some strips, then attaching some caps. So here's a torus built from one cup. Then you attach this orange strip and that green strip. What's a strip? It's a disk that's attached along two intervals on its boundary. And then you attach one cap, the purple cap. You count. V minus E plus F, that's the number of cups minus the number of strips plus the number of caps, or cups, saddles, and caps. You look whether the surface is orientable or not, and you look at the number of boundary components. So here I get 1 minus 2 plus 1, that's 0. That's the same as for this with a disk glued onto the boundary. They both have no boundary, and they're both orientable, so they have to be the same. Well, I mean, actually, it's not obvious that they're the same. Here's another one. This I drew with 2 disks. I'm thinking of having 2 of these cups. Then I attached 3 strips, no caps. So that was 2 minus 3 plus 0 minus 1 gives me this surface. Okay. So I thought I would end the section with some announcements about things that are weird extrinsically in dimension 4. And then we'll go back to being more concrete in a second. In R3, this knot here is the only one that's the boundary of a disk. Okay, well, that's obviously the boundary of the disk, but none of the others, and no other knot you draw is the boundary of a disk. It's sort of an exercise. On the other hand, there are non-trivial knots in R3 which bound disks in R4, meaning in this half space where W is bigger than or equal to 0. These 2 bound smooth disks in R4. I will draw both of them later in the talk, actually. On the other hand, there are knots in R3 which bound continuous disks but not smooth disks in R4. Locally flat disks but not smooth disks. So this one bounds a locally flat disk but not a smooth disk in R4. Okay. As a consequence of that theorem, there are spaces that are topologically the same as R4, homomorphic to R4, but not diffeomorphic to R4. So these are the topics of lectures 3 and 4 in the lecture series. So we'll do a significant part of proving that in the later lectures. Actually, there are uncountably many such things of this form, and this is something unique to dimension 4. So dimension 4 really is quite strange here. Okay, so coming to the rest of the talk, I want to talk how to visualize these smooth disks when they exist, and some more examples of knots that bound locally flat but not smooth disks, and a few words about how this is proved, and some open problems. Okay.
I'm a little confused what you mean by dimension. The surface is a 2-dimensional object intrinsically.
Yeah,
it's a 1-dimensional, but dimension 4 seems to be the spatial state.
The ambient, that's right. So intrinsically, we've completely understood surfaces on the previous slide. So my question about the extrinsic topology of surfaces, and that's what's weird in dimension 4.
Dimension 4 being the space.
The ambient space, that's right. Dimension 4 is the space that the surface is sitting in. That's a great clarification. Thanks. More questions? That was about the existence problem on the previous slide. The uniqueness problem is bad too in dimension 4. In R4, curves can't be knotted. There's space to just sort of move them around each other. But surfaces can be knotted. So knotted again means that they're intrinsically the same surface, but extrinsically they sit inside R4 in different ways. Question, suppose I had 2 smooth surfaces that were continuously isotopic. They're isotopic through if my fluid flows continuously, I can have my fluid flow continuously and take one surface to the other. Does that mean that I could get from one to the other smoothly? Okay. So the existence of a continuous isotopy implies the existence of a smooth isotopy. So it's like with thinking to ourselves, like, does this happen? You have your surface, and it moves around, and it gets non-smooth at some point. It's got all spiky. It's not very non-smooth, but it's visually non-smooth. And then I got to a different surface, by going through this one that I couldn't get to without. Okay. In R3, that doesn't happen. So the reason you can't visualize this happening is it doesn't happen in R3. If 2 smooth surfaces are related through continuous, reasonable continuous embeddings, they're related through smooth embeddings in R3. But in R4, this does happen. Pairs like that are called exotic. So I said I was going to explain what an exotic pair of disks is. I haven't said how these are disks, but this is what it means that they're exotic. They're related continuously but not smoothly. The first examples of this were for non-orientable surfaces in 87 by Khovanov, Craig, and Vero, and their proof used earlier work of Friedman and Donaldson that involved PDE, related to last year's Minerva lectures. But I wasn't here, so I don't know exactly what happened in those lectures. It's open whether there are closed orientable surfaces where this happens in R4. Disks are not closed. I'll give you examples of disks. So that's a sort of well-known open question, like spheres. OK, coming. I'm going to talk about some knotted spheres. We'll talk about some exotic surfaces of the boundary, and then just a few words about this proved. We're doing great for time. By the way, these are actually the same. So these are smooth. The left and the right are smoothly the same in R3. So this picture was exercise. This picture is a little misleading. Great. OK, so visualizing smooth surfaces. We're going to have a slide about global warming, couple of slides about surfaces in space. I'll talk about some ribbon disks. This is all about different ways of visualizing surfaces. And then we'll talk about some knots that don't bound disks, the exotic pair I promised you, and a non-orientable version exotic thing. OK. So this is probably a good time for me to say opinions expressed in this talk are those of the speaker and not necessarily those of the National Science Foundation. So we've been emitting carbon dioxide into the atmosphere, and that's causing global warming, and that's causing the sea level to rise. So as the sea level rises, we have this surface that's been floating somewhat mysteriously above the sea. And as the sea level rises, more of the surface is submerged. So for different heights of sea level, that's my number zeta here, there's a part of the surface that's below the sea and a part of the surface that's at sea level. So we're going to watch what happens to those as the sea level rises. I think that's next. Click. So the part in dark black is the part at sea level. And of course, you can see what's below. You see they sort of dance around. Most of the time, not much happens, but sometimes, like right there, they merge, and then it's going to disappear, and they merge, and that one's going to disappear. So this part below sea level just changes in a nice, simple way. It changes by an isotopy, except when you go through a critical point of the height function, a local min of height or a saddle. It's a saddle point or local max of height. If I just give you this movie of level sets, the movie of S zetas, the parts that are at the sea level, that's enough to build up the whole surface. If I give you precisely the movie, I give you precisely the surface. But if I just give you a sketch of the movie, I give you enough to build up the surface up to isotopy. So here's the movie from this isotopy. We started with nothing. A circle was born. Another circle appeared. This circle split into two. This circle split into two. They move around for a while. These two circles merge. Those two circles merge, and then they die. OK, let's just see the movie doing that while we have this on the screen. Haha, wrong place to click. How about here? There it goes. OK, merge. That one's born. Splits. That's like that one. They wander around. Wander around, those two merge, that was going to there, merge and disappear and disappear. Great. The same thing works in R4, but now the C is four-dimensional. It's everything below some level tau, and the surface of the C is the part where it's a three-dimensional thing where it's equal to tau. And now, because I'm using t and tau, you're sort of inclined to think of it as the time, which is how we were thinking of it before. So for example, here's a very simple sphere, coordinates, given in coordinates up there. It's a two-dimensional sphere in R4. And if we look at the corresponding movie, it looks like that. It's a movie of curves in R3. So we can draw that. Let me skip ahead one. So we can draw that. What happened in our movie? We had nothing. A circle was born. It wandered around for a while, and it disappeared. And this always works assuming that the time coordinate t on the surface passes the second derivative test, meaning the second derivative matrix is always invertible, or the determinant of the second derivative matrix is non-zero. So functions like that are called Morse functions. I didn't say it on the slide. That's fine. And up to isotopy, this movie determines the surface. So I can represent my surface just by drawing a sequence of knots in R3 like this, finite sequence of knots in R3. Okay. And this always works for smooth surfaces. Thought I would give you another example. Here's another movie. This is from someone I don't know, Inoue, from 2010, paper describing a surface that was written down by Emil Arden in 1925. So parts of the paper have a long history. This is a movie that starts with nothing. A circle appears. We went through a local min. Another one appears, another local min. They wander around. We go through a saddle. They merge. We go through a different saddle to get two different circles. They wander around again, and they disappear. This surface is actually a surface of revolution. Oh, sorry, I was going to tell you. This is a sphere. How do I know it's a sphere? We had 2 births, 2 saddles, and 2 deaths. So the Euler characteristic was 2 minus 2 plus 2. That's 2. And I compare that with my model surfaces. That tells me that G is 0, and so this is a sphere. See which surface on the list has the right numerical invariance. Well, you also need to know this is orientable, so maybe that's a bit of a puzzle of why is this surface orientable. Because you don't. Because this is 2, you don't need to know that. There are no non-orientable surfaces of Euler characteristic 2 connected. Thank you. This has been a very good audience so far. You know, you're in this audience and you sort of know everything the idiot speaker is saying, and it's really tempting to kibitz, and there's been none of that, so I'm very impressed. I'm not sure I would be so well behaved. This sphere is knotted. On a surface of revolution, it doesn't look at all like that, but I mean there's some arc like this that's being spun around the xz plane in R4. I wrote down coordinates in the supplement online if you want. Okay. So another pair. So let's do this for disks. So I've been looking at closed surfaces so far. But in the moving, if I want to think about a surface with boundary, I'm going to think that the boundary is at time t0. The boundary of the surface at time 0, and the rest of the surface is time before 0, it's below 0. So it's like in the 3-dimensional space, I've got the boundary up here, and the surface is all below. So here is a ribbon disk. So here's I know what ribbon is. I'm going to say what ribbon means in the next slide. But here is a disk. I start with nothing. A circle is born. Another circle is born. They move around for a while. This and that are the same picture. You can just untwist all of those, and then you pull that part through here and separate them. So it's just that motion. And then I do a saddle. I can't reach, but right up at the top there to get this thing. So this is a surface whose boundary is this knot. Surface in R4 whose boundary is this non-trivial knot. It's a disk that's by the same Euler characteristic computation. If I look at the same movie but backwards, so just read it backwards like this, what information did I need? I needed to know where the saddle was going from here to there. The saddle was this arc, and then, okay, the circles just move around and disappear. So the interesting part of the movie was entirely encoded in this arc. Okay, so this is a picture of a disk, and here is a picture of another disk. Okay, and these disks are not isotopic REL boundary. So you can't turn this disk into that disk without moving around the points in the boundary knot itself. That's a theorem. I mean, that's not obvious. I guess that's a challenge problem for the graduate students. Or ask me later. This was maybe an unsatisfying way of understanding surfaces in 4 space, so let me try to give a second way of visualizing surfaces in 4 space in case you like it better. So a ribbon disk is a disk in 3 space. We're back to real pictures you can visualize, an actual picture in 3 space. Here's a ribbon. with only ribbon singularities. What's a ribbon singularity? One part of the disk, viewed as a ribbon, pokes entirely through the interior of a different part. So you cut a slit in this yellow part and just poke the purple part through it. You can kind of build this with an actual ribbon where you start cutting slits and poking parts through other parts. So good terminology. Okay, I said that. If you take the yellow part here inside the dashed line, and you push the disk in here a little bit into the fourth dimension, just take your finger and like poke it into the fourth dimension, so the boundary of this circle doesn't move at all, but inside it gets all poked a little bit in. Then I no longer have this intersection because the blue part is still living inside my usual R3, and this inside the yellow is now poked in the fourth dimension. And you do the same thing there, but to the blue part inside that disk. So the parts inside the dashed circles get poked a little bit into the fourth dimension. Then this is an embedded disk in R4. And its boundary didn't change. I didn't do anything to the boundary. So it's a embedded disk in R4 with boundary, this not. So here's another challenge. Well, this is the same as one of the two disks I drew above. Which one? There's a conjecture that if a knot bounds a disk in R4, then it bounds a ribbon disk in R3. You can draw the knot and a disk in this way. So that's called the slice ribbon conjecture, and I think that's probably the most famous open problem in knot theory, though everybody's allowed to have their own opinion on which are the best knot theory questions. But anyway, that's a very famous open question. Does this, if you understand this picture, is that enough to understand all disks with boundary knots? Or all knots that bound disks? Sorry?
Do you think it's true or not?
Let me punt that till the end. I will not answer that question at the end of the talk. Here's another ribbon disk. So if you take a knot, here's a knot, and you take its mirror, and then you just join them up like this. This is called a connected sum. I'll give another connected sum later in the talk. The connected sum of a knot with a mirror always bounds a ribbon disk. That's another exercise. Exercise, unless I say otherwise, is something you could actually do. If you take that, you can now grab at another pair of end bits there and twist them up. You could do that several times if you want. This is called a symmetric union. This is like a sort of terrible operation because it depends on the diagram. Somebody staring at my slide ahead of time, this is actually the unknot. This is not. This is an interesting knot. This is called the Kinoshita-Terasaka knot. Okay, and these symmetric unions are always ribbon. They bound ribbon disks. Okay, this is the boundary of ribbon disk. I attempted to draw it. This is where you see that the schematic is actually clearer than the nice 3D drawing. Okay, but here's, you can see sort of the disk poking through. This is poking through there, whatever. Here's a different view of the same disk. We learned some things from this picture. One is that you don't want me to repaint your car. If you take the pink purple is the fourth dimension. So the purple part is all in the boundary R3. And the pink, the pinker it is, the more it's pushed into the fourth dimension. So I transition sort of suddenly so I get the picture to work. But this is embedded in R4 because, for example, up there, it's blue poking through pink. Or here, it's blue poking through pink. OK, that's pink, but this part was blue, and so on. So the boundary didn't change, and this becomes embedded. Fine. Again, it's somehow hard to see. The schematic's a little better, I think. OK. Some disks that don't exist. So knots that bound disks are called slice. That's why this was the slice ribbon conjecture on the previous, well, this 2 slides back. Most knots don't even bound continuous disks. Continuous means locally flat. For example, there's a theorem of Fox and Milner who I thought of like putting the star 62 or whatever by everybody who had been a Princeton graduate and every day. I didn't do that, but anyway, they were at Princeton at the time. If a knot bounds a disk, then something called the Alexander polynomial has a special form. If you don't know what the Alexander polynomial is, I'll define it and give one construction in lecture 3, so we'll come to that. This is a 3-tiger slide, so it's OK if it uses some stuff. So for example, these knots don't even bound continuously. So those are the first 2 non-trivial knots, the trefoil and the figure 8, because the Alexander polynomial doesn't have this form. There's an amazing converse, which is also the topic of lecture 3, due to Friedman, they're written down in the book of Friedman and Quinn, that if the Alexander polynomial is 1, then the knot does bound a locally flat disk. So that's the main topic of lecture 3. So this is like kind of the main way people produce topological disks in the literature. Some knots bound continuous disks but not smooth disks. So these both have Alexander polynomial 1, and therefore they bound topological disks by this Friedman theorem. But it turns out they don't bound smooth ones. This was proved. This is attributed to Akbulut, though I think not published from '83. This is the Whitehead double, positive Whitehead double of the positive trefoil. This is the Conway knot. That's the local Conway, of course. That was proved by Lisa Piccirillo in 2018, that it doesn't bound a smooth disk. There are simple knots which the answer isn't known. So this and that look pretty similar. The difference is that twist there. This is a negative Whitehead double of the positive trefoil. And this does bound topological disk by the theorem of Friedman's, but it's not known if this bounds a smooth disk. That's another famous open question. This one doesn't bound a smooth disk by a theorem from 2022 of these excellent group. It's not known if it bounds a topological disk. So like there are very simple knots. This is the 2-1 cable of the figure 8 knot. Right? This is similar to that knot on the top. They're very simple knots for which we don't know the answer to these questions. I'm saying something more. What am I saying more? Yeah, I'll skip that. There have been interesting computer search in the last few years, so that's another thing, and some hope to attack some famous conjectures with computer search. So that's another way in which this subject is timely, and the computer assistance is getting better, and maybe we'll answer some of these questions, though it hasn't yet. Great. OK, so summary, the existence problem is a mess. What about the uniqueness problem? So let's give an example of non-uniqueness. So here's a knot. If I just do this band, it turns out this falls apart into a 2-component unlink. If you can see that, your visualization is way better than mine. But if you smooth it out here, you can pull it through there, and you pull that through there, and you can imagine it all falls apart, and it does. Alternatively, if you do that disk, then the whole thing falls apart. So this represents a disk by using this strip. It represents another disk by using instead this strip. So you choose blue or yellow. And again, this is a theorem that I mentioned at the beginning, that this pair is exotic relative boundary. That is, there's a continuous isotopy taking one to the other, identity on the boundary, but there's no smooth isotopy doing that. So this is another instance of difference between smooth and non-smooth topology for the uniqueness question now in dimension 4. Okay. This relative boundary, I think, annoys people who are not topologists. So, and Hayden and Sundberg were like young at the time, so I guess this also annoyed them. So they gave an example, just tweaking that one, which is absolutely exotic. So you take now blue and brown or yellow and brown. Okay, so that gives you, again, 2 disks. If you do the blue and brown, this falls apart into 3 unknotted circles, unknotted, unlinked circles. You fill them with disks. So this is a picture of a disk. This is a picture of a disk. And those are absolutely exotic, meaning there's a continuous isotopy taking one to the other, but there's no smooth isotopy, even not fixing the boundary, taking one to the other. Said that they only prove this if there are enough twists here, because otherwise they would have had to do some proof that their numerical computation worked the way they think it worked. But it's true. It's almost, it's certainly true without more twists anyway. Okay, I thought I should mention a theorem of mine here. So that's what this slide is for. You take the same example, but you tweak it a little bit. So this is a little slightly different knot from that one. And you put in these 3 these three bands here. So I do these three brown ones. I get back to that picture without the extra thing on the side. Then you do blue or yellow. So three brown, or say black bands plus blue or yellow gives you a surface. This is a non-orientable surface. It's this non-orientable surface. That's a sort of challenge problem exercise. And this pair is non-orientable surface, exotic relative boundary. We didn't bother doing the absolutely exotic thing because, I don't know, we're too old. What was I going to say about this? Who knows? This is a very modest extension of what they proved. So this is not a big deviation. What they proved, we have to notice that some things also work for non-orientable surfaces. Okay. Say it again? To distinguish them, Khovanov homology. Other questions?
Oh, I was just say the parity of the Euler characteristic
Is different? No, I think it's okay. I think it's okay, right? Let's argue about it later. Closed surfaces. These are all surfaces with boundary. I said there's a theorem of Fanash, Craig, and Vero that there are exotic copies of this thing. It's RP2 connects some 9 RP2s with orientation reversed in R4. They didn't describe them the way I did here, though. That's probably possible. The description is less explicit. And I think from the original paper, at least, it wasn't clear which pairs are not isotopic, which pairs are exotic. They construct infinitely many that fell into finitely many something classes, and so they knew that most of them were different, but they didn't actually say which ones. This sort of game in 4 manifolds, you end up often with these big connect sums and trying to make it smaller, so Fanash got it down to 6. If you really go outside R4, there are lots of orientable examples. The first reference I know is from Fintuschel Stern from 97. These are both using gauge theory. These are both using PDE. All of this is. There's a recent theorem, Miyazawa, which goes down from this 9 RP2s, get rid of all of them. So there's an exotic pair of RP2s in R4. This connected some of the standard RP2 with something that's built from this pretzel knot. You can tell it's a pretzel knot because it's got little salt cubes all over it. They turn out not to show up very much in the proof. That's another, there's been remarkable progress in the last few years on understanding these sorts of questions. Okay, so last 7 minutes, say a few words about the strategy and a few words about open problems the rest of the course. Strategy. So the idea in most of the subjects, you're going to capture some of the topology with algebra somehow. So the tool we'll use in this course, and it proves many, though not all of the theorems from earlier, is Khovanov homology. What it does is to a knot, it gives you a collection of abelian groups indexed by pairs of integers. So this is the example. Maybe this is for the Hayden-Sundberg knot. I actually don't remember. So for each point in the plane, there's a group. The ones that are not drawn, the group is trivial. Here's the groups at various different lattice points. If you have a surface connecting one knot to another, you get a map of abelian groups. So you think of surfaces or cobordisms as being like maps of knots, and it turns those into maps of abelian groups with a grading shift. So the second coordinate, the height, the y coordinate in this picture gets shifted by the Euler characteristic. Now we're going to construct all of that in lecture 2, or at least the first part of that in lecture 2. These are invariant under isotopy of the knots or the surfaces. So doesn't change if you do an isotopy. So for instance, if you compute that the maps associated to 2 different surfaces are different, the surfaces are not isotopic. And if you could prove that there's no map from these groups to those groups, then there's no surface. Okay, you're very generous audience. This is, of course, bullshit, right? Because there's always a map of abelian groups, the zero maps. You need some reason the map can't be the zero map. But you have some non-triviality result for the map, and then you can prove that there's no surface. So again, we'll spell out some of those techniques in the next few lectures. Okay, I thought I'd end by pointing out that this is a field that has a lot of problems. These are the problems I stole from a new forthcoming problem list called K3 coming out January-ish from AMS. Much of it, so this is building on a famous problem list of, or revising, inspired by a famous problem list of Rob Kirby from the 80s and 90s, K1 and K2. And it has 365 problems in it. I think that was a coincidence. But if you solve one a day, you will have made, wiped out our whole problem list in a year and had a significant impact on the subject. Yeah. So these are just some screenshots from it. OK. So a few relevant problems from it. I already mentioned the sliced ribbon conjecture is every slice knot bound a ribbon disk. A sort of cursed variant of that is if it bounds a ribbon disk, is every ribbon knot a symmetric union? Do all ribbon knots arise this way? I have no idea if this is true, and I think the community doesn't either. So that was Zoltan's question that I'm not weighing in on. This is believed to be false. It's believed there are ribbon knots that are not symmetric unions. But it's very hard to study symmetric unions because they're much less geometric than you think. I mentioned this one also, are there exotic pairs of closed orientable surfaces in R4? Another one that came up implicitly is every knotted RP2 in R4, it doesn't have to be exotic, just knotted, is it the connected sum of a standard RP2 with a knotted 2-sphere? These are all questions that there are sort of plausible attacks on at the moment, so at least it's conceivable somebody will prove something about. Unknotting number. So I want to tell you another conjecture. So here's the unknotting number. It's the number, so if you let a knot pass through itself, you can always turn it into the unknot. So there, whoops, it passed through itself. I got the unknot. This one is no longer knotted. The minimal number of times you have to let it pass through itself is called, to get the unknot is called the unknotting number. So this one had unknotting number 1, well, before the movie, I guess. Here's one that has unknotting number, well, less than or equal to 2. If you change those two crossings, you get this thing, and you can convince yourself easily this is the unknot. Maybe it's unknotting number 1. It doesn't actually, but it's not clear how you would tell that. This movie gives you some sort of surface and force space, so this question, the unknotting number, ties pretty closely to the study of surfaces. I won't say that with short time. It's also called the Gordian number after the Gordian knot. So here's another problem. So connected sum, you tie a knot, you then tie another knot in the same string, and you glue the ends together. It's the connected sum of knots. Question, is the unknotting number additive under connected sum? That is, if I want to tie 2 knots and unknot it, can you do it faster than unknotting the first and then unknotting the second? And the answer is obviously you can't, right? I mean, don't be ridiculous. So this is not actually an open question. It was solved and proved in 2025 that you can sometimes by Mark Brittenham and Susan Hermler. Here's their example.
Is there proof to one that you just gave?
No.
Oh, no, the answer is...
The answer is the other direction. The obviously part is false. That's right. And Brittenham will talk about this here, I think this, here in November. So it's an ad for the topology seminar on November 13. We changed the problem, I think, so. What's a great question. This unknotting number is not known. Another question is the unknotting number algorithmically computable? Is an open problem. And nobody has, I think, any reasonable strategy for answering that. Here's some irrelevant open questions in my last minute. Are all knots trivial? If you take any non-wild knot, continuously you can unknot it. You just pull it really tight till the knot disappears. You watch that happen. That's not locally flat, but if you get the locally flat, all knots are trivial. So this is a question, sort of an analysis question. Are there any sufficiently wild knots that you can't do that trick to it? That's open. Suppose you have a pearl necklace. Okay, do sometimes. How many pearls do you need to tie a non-trivial knot? The conjecture is you need at least 15 pearls. This is a trefoil if you sort of trace it around, right? I drew it so the pearls were clear, but the knot was a little hard to see. There's a 15 pearls conjecture. We said the unknotting number is not additive under connected sum. What about the crossing number? This is 3 crossings. That has 4 crossings. Can you draw this with fewer than 7 crossings? Well, not this one, but that's an open question, very open. Do I have one more? No, just a remark that if you don't mind a factor of 152, the answer is known. But it's a bit of a ways from 152 to 1. OK. I'm out of time. So this slide is just the same as the beginning, but with a little bit of prerequisites. So for example, for next week, if you know about abelian groups and quotient groups, you should be OK for next week. And then stuff is sort of cumulative. But if you know something about covering spaces the week after, and then a little differential geometry the week after that, and then stuff gets a bit harder after that if we stick to schedule, which we very likely won't. I think I'll stop there. Thanks very much for listening.